Good day to you all. I hope you are all doing well. I welcome you back to our integrated science class. Today, God willing, we're going to end the topic that we've been looking at, that is electricity. In our previous session, we started talking about transformers. As a quick recap, we said a transformer is a device which changes the magnitude of the voltage of an alternating current. A device which changes the magnitude of the voltage of an alternating current. We said that you can also define a transformer as a device which increases or decreases the voltage of an alternating current. We went on to talk about the fact that we have two types of transformers. We have a step-up transformer and a step-down transformer. And we said that a step-up transformer is a transformer which increases the voltage of an alternating current by decreasing the current. And then a step-down transformer is a transformer which decreases the voltage of an alternating current by increasing the current. And we looked at some properties of step-up transformer and step-down transformer. So these were some of the properties we talked about. So for step-up and then step-down, when it comes to the number of turns, we said that the number of turns in the primary for step-up is lesser than the number of turns in the secondary. But for step-down, it's the opposite. So the number of turns in the primary is greater than the number of turns in the secondary. And then when it comes to the voltage, the primary voltage is lesser than the secondary voltage. Over here, the primary voltage is greater than the secondary voltage. And in terms of current, the primary current here is greater than the secondary current. And over here, the primary current is less than the secondary current. So these are the properties we came across under the two types of transformers, step-up transformer and then the step-down transformer. We're going to continue by looking at energy losses in transformers, how energy is lost in a transformer, and then ways of minimizing the energy losses. And then we'll continue to look at some relevant equations under transformers, and that will lead us into the last aspect, which is calculations. In transformers, so when energy is flowing through or passing through a transformer, some of the energy that is generated is lost. And we're going to look at some of the causes of the energy losses. So as current is passing through a transformer, some of the energy that is generated is lost. So let's look at the causes. So causes of energy losses. One cause of the energy loss is the resistance of the copper wire that is used in the secondary and the primary coils. So the resistance of the copper wire that is used in the primary and the secondary coils. Now, if the resistance of the copper wire is high, then the energy that will be lost in the copper wire will also be high. So the higher the resistance of the copper wire, the higher the energy losses. So in order to reduce or minimize the energy that is lost through the copper wire, it means that you must use a copper wire that has a lower resistance. For a copper wire to have a lower resistance, it must have a higher thickness. So it means that instead of using a thin copper wire, you should rather use what? A thick copper wire. So that is the way of minimizing the energy that will be lost in the copper wire used in the primary and secondary coils. So the first cause is the resistance of the copper wire in the primary and secondary coils. As I said, the higher the resistance, the higher the energy loss. So the higher the resistance of the copper wire, the higher the energy loss. So how do you minimize the energy that is lost in the copper wire? As I said, this can be minimized by using a thick copper wire instead of a thin copper wire. So this can be minimized by using a thick copper wire instead of a thin copper wire. Okay. So that is how you minimize the energy that is lost in the copper wire used in the primary and secondary coils. Now, the second cause of energy loss is what we call the leakage of magnetic flux in the primary coil. So that's the second cause. So leakage of magnetic flux in the primary core. So leakage of magnetic flux in the primary core. So I'll tell you what a magnetic flux is. When I say magnetic flux, it's just a number of magnetic field lines in a given area. So the number of magnetic field lines in a given area. How do you reduce the magnetic flux leakage? This is done by shielding the ion core. So this can be minimized by shielding the ion core. As a note, say that the magnetic flux is the number of magnetic field lines in a given area. Now the third cause of energy loss in transformer is what we call eddy current. So eddy current is the third cause of energy losses in transformers. Now when I say eddy current, this is the energy induced. The energy induced in the ion core as a result of changes in the magnetic field. So energy induced in the ion core as a result of changes in the magnetic field. That's what we call eddy current. Okay, what is eddy current? So it is the current induced in the ion core as a result of changes in the magnetic field. So the current induced in the ion core as a result of changes in the magnetic field is what we call eddy current. So that is another cause of energy losses in transformers. When this current is induced in the ion core, it will result in loss of some of the energies that are generated. And this can be minimized by laminating or shielding the ion core. So this can be minimized by laminating the ion core. can also say by shielding the ion core. Okay, so that is the third one, eddy current. Now the last course we're going to talk about is what we call hysteresis. 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 We talk about a process where there is an alternate magnetization and demagnetization of the ion core as current passes through it. Anytime a magnetic field, I've talked about alternating current, when alternating current is flowing, because there is change in magnitude and its polarity, magnetic field is generated, and that magnetic field will lead to magnetization of any magnetic substance within the magnetic field. So because the core is made up of iron, which is also a magnetic substance, the magnetic field that is generated around the core induces magnetism in the ion core. So at a point, the ion core becomes magnetized. At another point, it becomes demagnetized. So, and that process is what we call hysteresis. And during the magnetization and demagnetization of the ion core, it results or leads in energy losses in the transformer. So that is the fourth cause, hysteresis. So can be asked, what is hysteresis? So it is the process whereby there is alternate magnetization and demagnetization of the iron core as current passes through it. So the process whereby there is alternate magnetization and demagnetization of the ion core as current passes through it. That's what we call hysteresis. How do you minimize this? So this can be minimized by using a soft ion core instead of a hard ion core. Okay, so this depends on the ion core as whether it is soft or hard. If the ion core is soft, then the process of hysteresis will actually be lowered to the barest minimum. So the rate at which the ion core becomes magnetized and demagnetized will be reduced, and also that will lead to a reduction in the energy that will be lost in the ion core. Okay, so these are some of the causes of energy losses and how they can be minimized in a transformer. So the first being the resistance of the copper wire. The resistance of the copper wire. There is a relation between resistance and area, cross-sectional area. Resistance is given as this: the resistivity, the length, and over the area. So from here, your resistance is inversely proportional to the cross-sectional area. Cross-sectional area. It means that the larger the cross-sectional area, the smaller the resistance. So that's why I said that to reduce or to minimize this, we make use of copper wire, which has a higher thickness. If the thickness is high, it means that the cross-sectional area will also be high. So if you have a wire of this is the cross-sectional area. And you also have one as this. This is a cross-sectional area. So you can see this is a thick wire, this is a thin wire. If the cross-sectional area is high, then the resistance will be low. So that is why, to reduce the energy losses in the copper wire used for the primary and secondary cores, you make use of a thick wire instead of a thin wire. So that if the wire is thick, it means that it has a large cross-sectional area, and therefore it will have a smaller resistance. And then the leakage of magnetic flux in the primary core. So this leakage is actually predominant in the primary core and not the secondary core. And to minimize that, you shield the ion core. So it can be minimized by shielding the ion core. And they talk of the eddy currents. It says the current induced in the ion core as a result of changes in the magnetic field. And that can also be minimized by laminating the ion core. And the last one being hysteresis, where there is alternate magnetization and demagnetization of the ion core as current passes through it. And that can also be minimized by using a soft ion core instead of a hard ion core. Okay, so these are the causes of energy losses in transformer and how they can be minimized. You may come across this in past questions, so take note of this. Okay, so we're going to look at the last thing under transformers, which involves calculations. So calculations. There are some important equations you're supposed to take note of, which will help us in questions under calculations. So let's look at some of the equations. Now, the number of turns in the primary and the secondary core is actually proportional to the voltage. So if the number of turns is higher, the voltage will also be higher. So the equation that connects the number of turns to the voltage is given as the number of primary turns over the number of secondary turns is equal to the primary voltage over the secondary voltage. So MP over NS is equal to VP over VS. So primary turns, number of primary turns over number of secondary turns is equal to the primary voltage over the secondary voltage. So that is the relation between the number of turns and the voltage. Now, let's look at the relation between the number of turns and current. A quick recap of what we looked at. Let's say, for instance, if this is a step down, or let's say a step up transformer. So the number of turns here is what we call the MP, primary. The number of turns here is the NS. The voltage here is the VP, and the voltage here is the VS. So the number of turns here is over here, this is a step up, so the number of turns here is higher than here. I'm saying that the number of turns is proportional to the voltage. So if the number of turns in the secondary is higher than the number of turns in the primary, it means that the voltage in the secondary is also higher than the voltage in the primary. But the reverse holds for current. I said that even here, even though for step up, even though the voltage is increasing, the current or decreases. So that we say, that's why we said that a step up transformer is a transformer which increases the voltage of an AC by decreasing the current. So here the voltage is increasing, but then the current decreases. So here the number of turns is inversely proportional to the current. So here this is the relationship. MP over NS is equal to IS over IP. So here there is an inverse. For the voltage, it is VP over VS, just like MP over NS. But when it comes to the current, the IS is rather up, and then the IP is down. Okay, so we can also come out with a relation that involves the voltage and then the current. I told you MP over NS is equal to VP over VS. So in place of MP over NS, you can also put VP over VS. So your primary voltage over the secondary voltage should be equal to the secondary current over the primary current. So you must take note of this equation. A question can be given which involves number of turns and voltage. So you use this equation. A question can also involve number of turns and currents. So you use equation 2. Question can also be given which involves voltage and current. So you make use of equation 3. Now, you can also be asked to calculate what we call power input and power output. Your power input occurs or is a power generated in the primary core, and then the power output is the power generated in the secondary core. In terms of current and voltage, when we're looking at electric energy and power, we said that one of the equations for power is equal to current times voltage. So in transformers, if you're asked to find the power input, as I said, that is the power generated in the primary core. So it will involve the current in the primary core times the voltage in the primary core. So the power input or the power input will be equal to the primary current times the primary voltage. And then the power output is the power generated in the secondary core. So that one involves the secondary current times the secondary voltage. So IS times VP. So your power input is the same as the primary power. The power output is the same as the secondary power. And the machines, we talked about efficiency. So if you have to find the efficiency here, your efficiency is is equal to the power output over the power input times 100%. So if you remember, we said that your energy, when we're looking at efficiency in under machines, we came across efficiency is equal to mechanical advantage over velocity ratio times 100%. We also say efficiency is equal to work output over work input times 100%. I said that this work output is the same as energy output, so this is the same as energy output over energy input times 100%. Okay. And we said that under electric energy and power, we say energy is actually power times time. So your energy is actually proportional to the power. So that is why under transformers, we said that the efficiency is the same as the power output over the power input times 100%. Times 100%. Your MP is equal to number of turns in primary core and then NS is equal to number of turns in secondary core. Your VP is equal to the primary voltage your primary voltage here is the same as the input voltage. Your VS is the secondary voltage. Which is also the same as output voltage. Your RP is the primary current. IS is secondary current. Your PI is the power input. PO is power output. And then the EF is efficiency. Okay, so these are the definitions of the various parameters in the equations we're going to use for calculations. Okay, so we're going to start looking at related questions. Question 1 says the number of turns in the primary coil and secondary coil of a transformer are 500 turns and 2500 turns respectively. If the input voltage is 120 volts, calculate the output voltage. So from the question, we have 3 sets of information. We have the number of turns in the primary coil and the secondary coil, as well as the input voltage. So it says the number of turns in the primary coil and secondary coil are 500 turns and 2005 turns respectively. Respectively here means that the 500 turns is for the first one, is the primary core, and the 2500 turns is for the second one, which is the secondary core. And then we also have the input voltage. So as part of the solution, we have the number of primary turns, now the NP, to be equal to 500 turns. And we also have number of secondary turns, that's NS, to be equal to 2500 turns. And then we have the input voltage. I told you that the input voltage is the same as the primary voltage. The primary voltage, that's Vp, is equal to 120 volts. And the question is asking to calculate for the output voltage. The output voltage is the same as the secondary voltage. Vs. So we have these three steps and you are calculating for this. From this information, you should be able to determine the type of transformer that is in play, whether it is a step-up transformer or a step-down transformer. If you are comparing the number of turns, the number of turns in the primary is lower than the number of turns in the secondary. So that should tell you that this transformer is a step-up transformer. Once the number of secondary turns is higher than the number of primary turns, it means that the transformer is a step-up transformer. You should the kind of value you should be getting for the secondary voltage. Once it is a step-up transformer, then you expect that the secondary voltage should be higher than the primary voltage. So if you do your calculation, you're getting an answer lower than the primary voltage. That should tell you that you are actually wrong. So the voltage we are going to calculate has to be higher than the primary voltage. Now, so this is a question involving number of turns and then voltage. So from the equations we've looked at, we're going to look at the equation that connects the number of turns to the voltages. So if you look at the first three equations, it is equation 1 that connects the number of turns to the voltage. So we're going to make use of equation 1. We have been given the number of primary turns, we have the number of secondary turns, we have the primary voltage. We've been asked to find the secondary voltage, so we make Vs the subject. So from equation 1, we have number of primary turns over number of secondary turns to be equal to the primary voltage over the secondary voltage. If you cross multiply, this times A should be equal to this times this. So you have N P Vs is equal to Ns Vp. We are looking for Vs, so we now divide both sides by Np. This will cancel out. So you have Vs to be equal to Ns Vp over Np. So we do our substitution. The number of secondary turns is 2,500 turns. So 2,500 turns times the primary voltage, which is giving us 120 volts. over the number of primary turns, which is 500. So you have 500 turns. So the turns cancel out. 500 will go into 2,500 5 times. So 5 times 120, that will give you 600 volts. So the number of the secondary voltage, or what we call the output voltage, is equal to 600 volts. 600 volts. And so that is for question 1. Okay, so question 2 is a transformer with 5,000 turns in its primary core is designed to work from a 250 AC mains to produce a 10 volt to ring an electric bell. A transformer with 5,000 turns in its primary core is designed to work from a 250 AC mains to produce a 10 volt to ring an electric bell. And it says determine the number of turns in the secondary core. So from the question, we have the number of turns in the primary core. The transformer is working from this 250 volts. From a 250 volt AC mains to produce a 10 volt to ring an electric bell. So the transformer is working from this voltage, or is receiving this voltage, and then it is producing or giving out this voltage, which is used to ring the electric bell. So the voltage it is receiving is what we call the input voltage, or the primary voltage. And the one that it is giving or producing is the output voltage, which is equal to the secondary voltage. So this is the input voltage, or the voltage is receiving. So that is the primary voltage. And the one it is producing or giving out is this one. So these represent the secondary voltage. Okay, so with the solution, we have the number of primary turns. So number of primary turns. Which is 5,000. And then we have the input voltage. That's the primary voltage. VP to be equal to 250 volts. The voltage it is producing, as I said, is the secondary voltage. So that is Vs, 10 volts. And then we have to find the number of turns in the secondary core. So we are looking for number of secondary turns. That is NS. Yeah, so that's what we are looking for. Also, from this information, you should also be able to determine the type of transformer that is used over here. Yeah, you can't use the number of turns to determine the transformer because we don't know the number of secondary turns. But if you look at the voltages, your primary voltage is greater than the secondary voltage. It means that the voltage, the the input voltage has been reduced by the transformer. And the transformer that decreases or reduces the voltage of an AC is what we call a step down. So because the voltage has been stepped down, it has been decreased, this transformer or the transformer used here is a step down transformer. And so for a step down transformer, you expect that the number of turns in the secondary will be lower than the number of turns in the primary. So from our calculation, we should get a value for the number of secondary turns to be lower than 5,000 turns. 5,000 turns. Okay, so from the question we have voltage is given and we also have number of turns. So the equation to use is still equation 1, because equation 1 connects the number of turns to the voltages. So in this case, we have the primary turn given, we have the voltages given, so we are supposed to make NS the subject. So still using equation 1, our number of primary turns over number of secondary turns should be equal to the primary voltage over the secondary voltage. So we cross multiply this times this should be equal to this times this. So NS times VP should be equal to MP times VS. We are making NS the subject, so we divide both sides by VP. And this VP will cancel out, and you have NS to be equal to MP VS over VP. You do the substitution. So the number of primary turns is 5,000. The secondary voltage is 10 volts. And then the primary voltage is 250 volts. The voltages cancel out. These are cancel out this. 25 goes into 500. That will be 20. And then 20 times 10 will give you 200. So the number of turns in the secondary coil is therefore equal to 200 turns. 200 turns. Okay, so question 3 says that a step-down transformer has 50 turns and 1,000 turns in its coils. A step-down transformer has 50 turns and 1,000 turns in its coils. If its primary coil takes a current of 3 amperes, calculate the current in the secondary coil. Okay, so this is the question. So if you don't know the properties of a step-down transformer, you will not be able to solve the question correctly, because we have 2 turns here, 50 turns and 1,000 turns. One of the turns is for the primary and one is the secondary. If you interchange them, then your solution will be wrong. Your solution will be wrong. So the question is, which of the turns is the primary? And then which of the turns is the secondary? We said that for a step-down transformer, the number of primary turns is higher than the number of secondary turns. So this was the property for step-down. The NP is greater than the NS. So the number of primary turns is greater or higher than the number of secondary turns. So that's the property for a step down. If it was a step up, then the number of primary will be lower than the number of secondary. Okay, so because you are dealing with a step down, the primary turn should be greater than the secondary turns. So of the two turns, 1,000 is higher than 50. So this therefore will be the primary turn, and then the 50 will be the secondary turns. So number of primary turns is equal to 1,000 turns. And then number of secondary turns, NS, is equal to 50 turns. So if you go and interchange these values, you make the primary turns as 50 and the secondary turns as 1,000. Your solution is actually going to be wrong. Okay. And then the question continues to say that if each primary coil takes a current of 3 amperes, so this is a current flowing through the primary coil, so that represents the primary current. So primary current IP is equal to 3 amperes, and then you have to find the current in the secondary coil, so that's the secondary current. IS. Okay, so the problem with this question is for you to identify which of the things is the primary and which one is the secondary. As I said, because you are dealing with a step-down transformer, the number of primary things should be greater than the number of secondary things. So 1,000 things is greater than 50 things. So the 1,000 is the primary and the 50 is the secondary. So we have a question involving number of things and then the current. So you look for an equation that connects the number of turns to current, and that is equation 2. So equation 2 connects the number of turns and then the current. So from equation 2, MP over NS is equal to IS over IP, where cross multiply NS IS is equal to MP IP. You are making IS the subject, so you divide both sides by NS. These cancel out, and so you have IS to be equal to NP IP over NS. We do a substitution. MP, number of primary turns, 1,000. So we have 1,000 turns. And then times IP. IP is 3 amperes. Over the number of secondary turns, NS, with its 50 turns. So over 50. The turns cancel out. This cancel out. 5 goes into 100 is 20. 20 times 3. That will give you 60. So 60 amperes. So the current in the secondary coil is therefore equal to 60 ohms. 60 amperes. Therefore equal to 60 amperes. Question 4. If a step-up transformer has 100 tenths and 2000 tenths in 8 coils. If the primary coil is connected to a 250 volt supply, calculate the voltage induced in the secondary coil. Okay, so solution. This one we have 2 tenths given, 100 tenths and 2000 tenths. One of them is the primary, one of them is the secondary. And the transformer is what? A step up. So for a step up transformer, what's the relationship between the number of tenths? For step up, the number of primary tenths is lesser than the number of secondary tenths. So primary tenths should be lower than the number of what? Secondary tenths. So 100 is lower than 2000. So it means that the 100 tenths represents the number of primary tenths and the 2000 represent the number of secondary tenths. So number of primary tenths NP is equal to 100 tenths. And then you have number of secondary tenths to be equal to 2000. Now the question says the primary coil is connected to a 250 volt supply. So the input voltage at the primary coil is 240 volts. So that's the primary voltage. That's 240 volts. And they have to calculate the voltage in the secondary. So that's the secondary voltage. So a question that connects the number of tenths to the voltage. So that is, we're going to use equation 1. Equation 1 connect the number of tenths to the voltage. So using equation 1, MP over NS is equal to VP over VS. A cross multiply NP times VS equals NS times VP. So this times that should be equal to this times that. You are looking for VS, so you divide both sides by NP. So that our VS becomes NS VP over NP. When I do our substitution, our number of secondary tenths NS is 2000. So we have 2000 times our VP is 240 volts. And then the NP primary tenth is 100. The tenths cancel out. The 2 zeros also cancel out that. So you got 20 times 240. I'll give you 4, 8, 0, 0 volts. So now I'll give you 4,800 volts in the secondary core. In the secondary core. Question 5 says a potential difference of 3.00 volts is maintained in the primary core of a transformer. The current in this core, so in this core means making reference to the primary core. In this core, so it's making reference to the primary core. So the current in the primary core is 1.50 amperes, while the secondary voltage is 2.00 volts. You have to calculate the current in the secondary core. So, solution. So we have the potential difference. Your potential difference is, as I said, when it comes to calculation, the potential difference is the same as the voltage. So the voltage in the primary core is the 3.00 volts. So that's the primary voltage. So our Vp is equal to 3.00 volts. The current in this core, that's the current in the primary core, is 1.5. So that's the primary current. Ip is equal to 1.50 amperes. And then it says while the voltage, the secondary voltage is 2.00 volts. So we have secondary voltage. Vs to be equal to 2.00 volts. And then the question is to calculate the current in the secondary core. So that's the secondary current. Is. Okay, so we have information involving voltage and the current. So you look for an equation that connects the voltage to the current, and that is equation 3. So equation that connects the voltage and the current is equation 3. So using equation 3, we have Vp over Vs to be equal to Is over Ip. You cross multiply Vs times Ix to be equal to Vp times Ip. We are making Is the subject, so we divide both sides by Vs. The Vs cancel out, and you have Is to be equal to Vp Ip over Vs. Do the substitution. Vp is 3.00 volts. Ip is 1.50 amperes. And then we have Vs to be 2.00 volts. So yeah, the volts cancel out. You multiply, divide, that will give you 2.25 amperes. Okay, so the current flowing through the secondary core is equal to 2.25 amperes. 2.25 amperes. So question 6, and this is the last question we are looking at. It says that a transformer can produce 24 volts from 40 volt supply. If the current in the secondary coil is 10 amps, calculate the current in the primary coil, the power input and the power output. So the question says the transformer can produce 24 volts from 40 volts. So this is the voltage that the transformer is going to produce, and it's producing from this voltage. So it means that this is the input voltage, the voltage that is coming into the transformer, and the one that the transformer is giving out, is producing, is the output. So the one that it is producing is the output voltage, and the one that is coming in is the input voltage. As I said, your input voltage is the primary voltage, and the output voltage is the secondary voltage. So our primary voltage is the 40, and then the secondary voltage is the 24. Okay. So that should tell you that if the voltage, the input voltage 40 and the output is 24, it means that the voltage has reduced. So the transformer here is a step down transformer. Okay, so we have the primary voltage, VP, which is the input voltage here as 40 volts, and the voltage that is being produced is the output voltage, where it is equal to the secondary voltage, Vs. You interchange the positions of these two voltages, you are wrong. And then the secondary coil receives current of 10 amperes, so that's the secondary current. IS 10 amperes. So the first question A is asking the current in the primary coil. So you have the primary current, IP. So we have information on voltage and current. So you look for equation that connects the voltage and the current. Equation connecting the voltage and the current is equation 3. So you use equation 3. So VP over Vs equals Is over IP. You cross multiply, you have VP IP to be equal to Vs Is. You are looking for IP, so you divide both sides by VP. You do so, the IP becomes Vs Is over Vp. If you do the substitution, the value of Vs is 24 volts. The value of Is is 10 amperes. And then the value of Vp is 40 volts. The voltages or the volts cancel out. This 0 cancel that. So you have 24 over 4, which is equal to 6. So 6 amperes. been asked to calculate for the power input. Power input. So from our equation, power input is for equation 4. Power input is the primary current times the primary voltage. So PI is IP times VP. IP we calculate 36, and the VP given is 240. No, the VP given is 40. So 6 times 40, that will give you 240 volts. Power is measured in watts, so that is 240 watts. So that's our power input. And then C, power output. Our power output, that's the power in the secondary coil, will be, that one is also equal to current in the secondary coil, secondary current times the secondary voltage. The secondary current was given as 10 amperes, and the secondary voltage as 24. 10 times 24. And that is equal to 240 watts. So you have the power output also being equal to 240 watts. What it means is that if you're supposed to calculate for the efficiency of this transformer, that is the power output over power input times 100%. It becomes 240 over 240 times 100, which is equal to 100%. And it means that for this transformer, for a transformer to be 100% efficient, it means that in that transformer there was no energy losses. But in most transformers there are energy losses, so hardly will you calculate for efficiency to be equal to 100%. What it means is that in most cases, your power output will normally be lower than the power input. And so for that, and therefore the efficiency will also be lesser than 100%. And so this brings us to the end of transformers, and for that matter, the end of the topic electricity. And this actually will also mark the end of our online sessions. Hopefully, school reopens next week. And so we're going to continue with the other topics when you guys come back. Until we meet again, continue to study assiduously for the upcoming examination. When school resumes, you're going to take series of tests and exams. So make sure you prepare to school. Until we meet again, have a blissful day. Bye.